outside. I think that's NCAT, which is in Greensboro.
Oh, I see. So they see us.
Yeah, they see a full.
I see from those two
yeah.
cameras.
It's a full duplex.
Not bad. So we can also hear them when they ask questions?
Oh, yeah.
So this seminar is always broadcast to Cherbourg?
Different places. Whoever. Depends on the interest.
Okay.
If they're interested, they hook in.
Oh, okay. So the signal is there. So
Okay, you're all set.
Okay, very good. Well, thank you all for coming and welcome to today's seminar. It's a pleasure to welcome among us Dr. Misha or Mikhail Beylkin from the Ohio State University Computer Science Department. And Misha went to Moscow State University before going on and getting his undergrad at University of Toronto in mathematics, and then went on and get his PhD at University of Chicago. He did his PhD with Partha Niyogi.
This is Network Control. Sorry to interrupt, sir.
Yeah?
We need to get a microphone check before we get started. We can just barely hear your audio coming through.
Can you hear me now?
We need to get that resolved before we begin.
Can you hear me now? Which one?
Your technician there needs to raise the volume on your microphone.
All right. Okay.
It's a terrifying technology.
It's terrifying technology. That's why it's called technology. To be terrifying. Can you get the our technician here?
But maybe they can hear me, right? I'm wearing a microphone, no?
We're okay?
We're okay.
All right, thank you. Thank you.
Once you think you have the level corrected, go ahead and just count to 10, please.
Okay, can you hear me? 1, 2, 3, 4, 5, 6,
I cannot. It's just very, very faint.
8, 9, 10? No?
Maybe you can take the microphone?
Can you hear this microphone?
That does sound better. The volume needs to come up dramatically.
Can you hear this microphone?
Yes, that one's great.
All right, very good. Let me just use this and then I'll go sit down and be quiet.
Okay.
Okay, so it's a pleasure to welcome Dr. Mikhail Beylkin from the Ohio State University Computer Science Department. Misha went to Moscow State as an undergraduate and then went on to get his degree in mathematics from University of Toronto. Then he went on to get his PhD from University of Chicago and worked with Dr. Niyogi. And he's been now at Ohio State for 2 years. And he's a recipient of a NSF Career Award. He's been doing a lot of very interesting work in learning theory, and he's going to share some of that research, or some of those research results with us today. It's a pleasure to have you. Thank you for coming, and welcome.
Thank you. Thank you for inviting me. And, so what I'm going to talk about today is sort of the work we've been doing for quite a while now. And it's basically about various geometric aspects of learning from labeled and unlabeled data. And this is joint work with Partha Niyogi, Vikas Singhwani, and Hariharan Narayanan. At least parts of it are, parts of it are joint work with different people. So the first thing I would like to say that so the first thing is that I would like to sort of make, before I start on this, let me put this away. I would like to make several points, and the first point is that the sort of idea of this work is that, in a sense, one can think about data as lying on some. So what do we have in sort of typical learning problem? We have some typically high-dimensional data. This may be images, this may be sound, this may be, text documents, and all of them are in some sense a high-dimensional data represented as high-dimensional vectors. But perhaps the true sort of nature of the data is not so high-dimensional. Perhaps moreover, there is some interesting geometric structure in that data. And I would want to say that in many domains, for example, in speech and some vision problems, data explicitly lies on a manifold, right? In many things, like, for example, like if you take an object, you take a camera, you rotate the object, the set of all images is parameterized by the set of rotations. It's an orthogonal group. It's a 3-parametric space, I think. And so this is clearly a manifold. So there are other examples like that. For example, in speech, you can model speech by having several tubes. Sort of, you put several tubes together, and you can model, at least you can model vowels this way. And now it's clear that you can have, I think, a pretty good representation of a sound from 3 tubes. And so basically how many parameters that 3 tubes have, its length, its width, like something like 6 parameters, roughly speaking. So basically you can model vowels as lying on some 6-dimensional manifold. But of course the actual sounds themselves are infinite dimensional in a sense, right? It's a wave. So in some domains it's pretty clear that you can model it by a low-dimensional manifold. In some it's less clear, it's less clear. But what I would like to say, for example, like something like if you look at something like handwritten digits, it's not completely clear that it's a high-dimensional manifold, but it's clear that it's some parametric space, and there are not too many degrees of freedom. If you have a 7, maybe there is a length of this lag of a 7, and the length of this, and the angle, and roughly that's kind of like a 7. So even though we don't know whether it's actually a manifold or not, or whether this question even makes sense, I mean, what does it mean to actually be a manifold? It can be modeled this way, and it's moreover, it's sort of flexible way of thinking about this. And what I would like to actually say that for all sources of high-dimensional data, true dimensionality is much lower than the number of features. And I would argue very strongly that this is true, at least for all sources of data which we encounter or can make sense of. And because if you really have 100-dimensional data or 1,000-dimensional data, it would look like noise, even there is a lot of information that you just can't. There is a curse of dimensionality in a sense. And another thing is that much of the data is highly nonlinear. And again, it's pretty clear. You look at something like rotations of an image, rotation of an object taking images of it, right? I mean, of course, rotation itself is a linear transformation, but when you take images of this, it's kind of a nasty thing. Shifting you're shifting like, an object and taking images of the shift. The shift itself is a simple transformation, but once you take images, it becomes highly nonlinear. And pretty much in everything, I think one can argue that the data is quite nonlinear. So in a sense, we have a lot of linear methods like principal components analysis and so on. But it would be nice to have something which sort of makes use of this nonlinear structure. Okay. And in a sense, I would like to argue that this has been sort of our point of view for some time now. And so that Riemannian manifold is sort of a natural, at least mathematical language for talking about these problems. And perhaps one may want to consider something slightly more general than just a Riemannian manifold. Maybe you want a Riemannian manifold. The Riemannian manifold is a manifold with a distance on it. And you may want to consider them to be together with a measure on this manifold. And maybe you want to also consider noise of the manifold. So you can imagine like something like a surface, and then there is some measure on it. Some parts have higher density than the other. So you're more likely to get examples from that part. And then maybe there is some noise of the manifold. You know, your measurement and other things are always noisy. So that seems like a very powerful model. By the way, one of the interesting observations is that a mixture of Gaussians, right, which is sort of this very classical object. Mixture of Gaussian is an example of that. When the manifold is actually zero-dimensional, it's a bunch of points, right, and you have noise of this point. So mixture of Gaussian is a special case of this framework. So this framework is quite general, I think, in a sense. Maybe even too general. Okay. So now what are the problems we want to address? So the traditional problems of machine learning is classification, regression, data representation, and clustering. You know, this classical problems. And what is the sort of idea? So this is our images, and we would like to, you know, classify them, represent them in some way, maybe in low-dimensional space, and cluster them together. And all of this are sort of based on some notion of similarity. In a sense, we want to say that this one and this one, well, okay, they don't look very similar, but they, in a sense, somehow we would like to argue that they're similar, right? They both belong to this class 1. So when we do clustering, we hope that all the zeros will come together in one cluster. When we do data representation or dimensionality reduction, we hope that after our projection, this will be close, and so on. So in a sense, all of this are based on certain notion of similarity between these objects. So, and this is a common intuition, that similar objects have similar labels. Now, how does shape of the data? So now you can imagine I have my manifold. This is where the data lie. And I want to see what can I say about the shape of this manifold and how will it affect this notion of similarity. And one idea, though there are two distinct assumptions can be made, or somewhat distinct assumptions in any case. And one is this manifold assumption, that is cluster assumption, and in a second I'll explain what they are. And I'll start with an example. You have 2 points. The question is, you know, suppose I want to do classification. This is class 1, this is class 2. I want to classify. Hopefully you'll agree that this is a good classification boundary, right? I mean, raise your hand if you don't agree with that. Okay. Yeah, I think there are some people who will argue, and, but I think most reasonable people will agree on this. Okay, now what about this? So suppose I tell you, here is the shape of my data, but I'm not telling you what the data, I'm just saying all my data lives on these 2 circles. Okay? Now, this is a red point, one class, this is a blue point, another class. So where should the boundary go now, sort of from just the most naive perception of this picture? It should sort of curve around, right? Like this. So basically, what does this illustrate? This illustrates that the shape of the data, the fact that the data has these 2 circles, it actually affects our notion of similarity. Right? So we thought that these 2 points somehow were like this, but once we see that the shape of the data, that actually changes our perception of where the boundary is. And that is something that we want to consider. Here is another one. So here you have 2 red points and 2 blue points, and the problem is to classify the black point. And again, you know, if you'll agree that it probably should be blue based on this, but now I tell you, okay, actually it's all on a curve like that. Now, okay, well, you know, this one lies between these 2 red ones, probably it should be classified as red. Okay, so again, we see that this manifold assumption changes the way we view it. Now, what is the difference with the cluster assumption? So cluster assumption is sort of a slightly different geometric assumption. And it basically says the following. Again, you have a similar situation, but now imagine that your shape is like this. Let's just say you have a uniform distribution here. Now you can say, well, this is sort of a blob, and this is a blob, and this is somehow roughly like two Gaussians, let's say. And these 2 points belong to the same clump, to the same Gaussian, to the same whatever. So they probably should be classified the same, and they should be classified differently. So that's what one might call the cluster assumption. Okay, and now finally the final point is that unlabeled data, you can sort of, you don't actually need to know the curve itself. You can just know some points on the curve, right? This is enough to reconstruct this curve, and this is good enough to be able to classify this as point as red. Okay, good. So this is a sort of the intuition, building up some intuition about how to think, or at least about one way of thinking about these problems. Now, let's see what happens. So this is actually an example. This is what a support vector machine does, right? Probably people know what support vector machine is. So this is the actual example. This is 1, this is 2. This is what support vector machine does. I mean, clearly it cannot do any better than this. It just gives you a linear boundary because there are just 2 labeled points, right? It doesn't know what to do with this unlabeled point. And now if we have our method, actually, this is what you can do. So basically you have this some sort of extra knob, and this knob actually sort of takes this unlabeled data into account. All right. So I hope I'll explain how it works in a little bit, but this is just to show. Okay, now I would like to sort of formalize this a little bit. And so you can imagine what I have is the following. I have a map x to y, and this is the map I want to estimate. And this may be my, if in the regression setting, that would be a map from x to real numbers. In classification would be binary, but I can still think about it as being x to r. And what do I want to say? I want to say that, in a sense, this map is smooth, varies nicely with respect to some sort of intrinsic structure of the data, with respect to the manifold itself. And I'll formalize this further in a second. But so basically, this is the sort of the manifold assumption may be said to. These functions of interest are smooth with respect to the underlying geometry. Okay. Now, so what is smooth? Well, what does it mean that the function doesn't vary too much? Basically, I take the function, I take the value at a point, I take a value at the nearby points, and I look at how much it changes over at each point, how much it changes when I go off a little bit, some sort of, deviation or whatever it's called. Then this is just at one point. And if you look at this difference, it's basically, what is this? I take a little ball, I take the difference, and I integrate this, and it's roughly like the gradient at that point. So the limit of this, if delta tends to 0, is actually the gradient. But then I want to see that at each point, right? So the total penalty is the integral over each point of this. So this is the total penalty. And now it turns out that the total penalty can be also written like this, when this is a Laplace operator. And this is being some sort of integration by parts. Does it make sense? Yeah, so maybe, so one way to think about it, if it's just one dimensional case, this is, the first part is integral f prime squared, from 0 to 1. And suppose you have boundary condition that the function is 0 here and 0 here. Then this is equal to integral of f prime prime, actually it's minus f dx from 0 to 1. This is integration by parts, right? So it's actually f prime f from 0 to 1, but boundary condition, if you put boundary condition, then this is a far generalized version of that. Okay. Now, what is this? Now, what if I want to do clustering? If I want to do classification, for example, what do I look at? Actually, it's kind of simple, right? You just do the following. You just look at probability of 1 given. Suppose it's a 2-class classification problem. Then you look at probability of 1 given x, and sorry about that. Probability of 1 given x, and you want this to be a nice smooth function with respect to the underlying manifold. And what does it mean, a nice smooth function? It means that this quantity is small. Okay. And so manifold assumption can sort of be reformulated in this form. It can be said that P of 1 given x, Laplace P of 1 given x, is small. So we want to have functions for which this quantity is actually small. That's a nice function. That's a function which don't vary much. Okay. Now I'll just this is a brief recap about Laplace operator. So Laplace, what is the Laplace operator? Is in real in Rn is just the following: it's the sum of squares of partial derivatives, and it's actually the only differential operator which is invariant on the translation and rotation, which makes it unique, right? Because it basically describes the what happens in sort of this what is the word, homogeneous. If you have homogeneous, say, heat propagation or wave propagation, anything like that, isotropic, yeah, that's the word. So that's why it appears in all this heat wave Schrödinger equations. And it's also a basis of Fourier analysis. So how is it a basis of Fourier analysis? Well, it's a basis of Fourier analysis in the following way. So one-dimensional Laplace operator is just a second derivative. So look at its eigenfunctions. What does it mean? That f is its eigenfunction. It means that f prime prime minus f prime prime equals lambda f. And if we consider it on a circle, that means that we have periodic boundary conditions. F of 0 equals f of 2 pi. Now, let's just think about what it means. It means that f prime prime equals lambda f, and solutions for that are sines and cosines, right? And then we have these boundary conditions. So the solution for that, well, actually, solution is like, yeah, it's e to the I. But so basically, solution for this is just the things like this: sine n phi and cosine n phi. Now, this thing we know from Fourier analysis. This thing form a basis for L2 functions on periodic L2 functions, which is periodic means just it's a function on a circle, right? So what is Fourier analysis? Fourier analysis is nothing else but a theory of eigenfunctions of the Laplace operator. Yeah, does it make? Please ask questions if there is anything is unclear. So basically, eigenfunctions of the Laplace operator form a basis, very natural basis of functions on a space. In this case, on a circle. And in fact, when we do Fourier analysis, we do nothing but considering Laplace eigenfunctions of the Laplace operator. And the nice thing is that, look at sine n phi. What is its eigenvalue? Well, eigenvalue, when you differentiate sine n phi twice, you get sine n phi times n squared, right? So the corresponding eigenvector is n squared. Eigenvalue is n squared. So what happens is when you differentiate it, you get n squared. And now the higher the eigenvalue, the higher the frequency, right? So the nice eigenfunctions, low frequency harmonics, have low eigenvalues. High frequency harmonics have high eigenvalues. So in a sense, we have this nice sort of ranking of these guys, of these eigenfunctions of the Laplace set. And they're ranked by their frequency, by their eigenvalue. Right. So the good ones have small eigenvalues, the bad ones have large eigenvalues. Okay, now on a sphere, let's say, there is no, it's not a Laplacian, it's a Laplace-Beltrami operator, what is known, but it's roughly the same thing. So basically, you take a function on a sphere, you define it on this tangent space to the sphere. This is general for any manifold. And you just take the ordinary Laplace operator on this tangent space. And now you see, of course, it varies from point to point. So then it's kind of different, but it's rough. I mean, it's basically the same thing. It's just on each tangent space, you have the same Laplace operator. And if you do this on the sphere, you actually get spherical harmonics. You're not a classical object. So this is a generalization of Fourier analysis for arbitrary manifold. Of course, this is all well known. These are classical mathematical objects. Okay, now the question is, so suppose we want to do some regression problem on a sphere or some classification problem on a sphere. Then solution can be very simple. For example, what can I do? I can do something like this. I can take a few harmonics. I can represent my function using this harmonics, and that's a good approximation of the thing, right? This is what people do in Fourier analysis. Signal processing, you write it as a sum of some harmonics, you cut off something, that's all. So you can do it on an arbitrary manifold. Of course, you can do any regression classification in this way on a manifold. So if you know the manifold before, then pretty much you are done. You can compute this. Okay, maybe it's not trivial to compute this, but maybe you can compute them, and then you do this. But the problem is, the thing is, in the problems which we're interested in, we don't know the manifold. For example, for something like images, in general, we have no idea. Or speech sounds or something like that, we have no idea what these are. So what do we do? So we actually construct something. So we reconstruct this manifold in some sense. And let me explain what it is. So before I sort of explain how to do it, let me just explain to you what a graph Laplacian is. And the graph Laplacian is the following object. It's a very sort of elementary thing from graph theory. Basically, it's the following. Suppose you have a graph like this. And on this graph, you have a function. So a function on a graph is just a value at each point. Yeah? So at each vertex, you have a number. And maybe these edges are weighted. It may be a weighted graph. Then you can construct the quadratic form in the following way. You just take a difference between each adjacent pair of adjacent vertices, and you take a difference. This is a graph Laplacian, this quadratic form, the matrix corresponding to this quadratic form. Okay? It's actually kind of similar to the adjacency matrix. So pretty straightforward, right? You just write this quadratic form. This is some matrix, and this matrix is a graph Laplacian. Okay. Now what I want to do, I have some points sampled from a manifold, and I want to reconstruct the Laplace operator on a manifold, but I don't know the manifold. I just have these points. What do I do? What I do is the following. We connect these points by an edge, nearby points by an edge, and there are various ways in which you can do it. You put weights, which are these Gaussian weights, on this, and then you play the following. You do exactly the same thing. You take the quadratic form. Right. So given a function here, so Laplacian is an operator, right? It operates on functions. And basically, given a function here, I would say that F transpose LF is equal to sum e to the minus x minus ij squared over t. This is just a Gaussian in the space. Times Fi minus Fj. And sum is taking over adjacent vertices. Yeah, actually, you can take over all, but it's better. For many applications, it's better, yeah.
Well, I didn't
understand how you extend the Laplacian to functions.
I mean, I've seen the Laplacian derives from the incidence matrix. If you've seen.
Yeah, let me go back one.
I just didn't understand how you extend
This is a Laplacian matrix, right?
Okay.
Now, what is a function on a graph? The function on a graph is just a vector. For each vertex, you have a number. How long is this vector? The length of this vector is the number of vertices, which is the same as the incidence matrix, of course. So this matrix acts on vectors, right? And so if you just apply it to f, this would be Laplacian applied to a function, and this is like f in a product LF. Yeah, makes sense? So it's the same. Quadratic form and this is the same. You just can think of matrices, so you can think about matrices applied to vectors. I prefer to think about functions because that's ultimately we're interested in functions. Okay. So you see, this is basically the construction. This may be my underlying space, which I don't see. It's invisible to me. This is the point cloud which I get from this space by sampling it. This is a graph which I construct, and this is a procedure, and this is my Laplace. Okay? I hope this is clear. All right, good. Now, okay, so now this actually leads to this sort of, so this is what we suggested, pardon you again, we suggested this 2001. So to use this for data representation, and the data representation, basically, here is the idea. You have this, you want to construct a map. So think about something like principal components analysis, right? You want to project and have some nice property of projection. So imagine that you can think about this as, if you try to minimize this, what does it mean? It means that points which were close together in the original space should come close together in the. So in a sense, this is preserves some sort of adjacency information, right? It tries to shrink points which are close together to that. And so basically, you want to try to minimize this. Of course, minimizing this, you just get constant function. Okay, that's kind of boring. Nobody wants a constant function. So then you take the next eigenvector of this. So when you minimize this, so the thing which actually minimizes is a constant function for which you get 0. Then the next thing, which is orthogonal, is some more interesting thing, the first eigenvector of this. Then you can take the next orthogonal, which is the second eigenvector, and so on. So you get this map from your space, or from the data, to some other space. And it has nice properties. In some sense, it sort of tries to preserve this clustering information. So yeah, this Laplace and eigenmap sort of thing. And maybe I'll show some let me show some pretty pictures. It's always nice to see some picture.
So what are the WIJs exactly? Those are the weights, I suppose, of the edges or something?
So WIJs here, if e to the minus
it's
distance,
weight,
right?
yeah.
Or sometimes you can just take it to be, 1 or 0 and just do the sort of hard thresholding. In practice, that works pretty well. Yeah?
What's the difference between this and local linear?
Embedding. I know the local linear embedding also try to establish some local linear relationship.
Yeah, so let me just, unfortunately, let me just do. So actually, local linear embedding is, so local linear embedding, this was actually the LLA and ISOMAP were the first two works on this sort of manifold estimation, dimensionality, manifold dimensionality reduction thing. So actually, local linear embedding is kind of hard to analyze, but you can sort of analyze it. In fact, we had it in our paper. It's basically, it turns out that locally linear embedding also, in a sense, computes the Laplacian. In some sense, you can show that it computes the Laplacian. But there are some aspects of which it makes it a bit hard to you can say that it roughly computes the Laplacian, but it's hard to prove that it converges. But yeah, in a sense, locally linear embedding also computes something quite similar. Sorry, oh jeez. Okay. All right. So let me just show this. So let me. So okay, you can see probably very well. So okay, this actual digit. This is actually MNIST, and so what happens is the following. So each digit, this is some. So MNIST, I think 28 by 28, so it's 700 dimensional something, 700 dimensional space. So you take each digit. This is a point in the 700 dimensional space, right? Because each point 700 coordinates, and this is PCA applied to this into 3 dimension, right? So each point here, the coordinate is just PCA, principal components analysis, and this is what it looks like. And you kind of see some classes are okay, but for some classes it's kind of a mess. Mostly it's a mess. In the middle it's kind of all a mess. So now. Okay, let's compare this to this. So this is actually the result of this algorithm, of our algorithm. And so you take this Laplace operator, and you take the first eigenvector, second eigenvector, and the third eigenvector. Well, first non-constant eigenvector. And this gives you 3 coordinates, and you embed. And the coordinates of which point is here. And you see, well, it's probably better. I would say. It's mostly better. I mean, in some places it's still a mess, but it's definitely in many places it's much cleaner. And actually, one thing which is kind of amusing here. Let me see if I can find this. Okay. So this is good. So you see 4, and this is 9, and this is 7, right? They're sort of layered like this. So can you guess why they're layered like that? I mean, if you write 4, 9, and 7, what do you see? Well, what is 9? It's 7 plus this, right? And if I remove the top, I get 4. So 9 is kind of in the middle between these two, right? So completing this, I get a 9, and removing the top, I get this. And you actually see that it captures. It captures it quite nicely. So it certainly captures something about the data, something about the shape. I mean, I wouldn't make too many far-reaching conclusions on the basis of, this 4, 9, and 7 phenomenon, but it's...
Did the same happen, for example, with 5 and 6, or 6 and 8?
I think 5 and 6 probably. I don't know, actually. Let's see.
Yeah, they're close.
Yeah, they sort of, 5 and 6, yeah. Sort of, yeah, I mean, it certainly captures something about the shape of this. I mean, yeah, so it's doing something, sensible, whether, okay. Okay, so, in any case, pretty, I'll have one more pretty picture, actually. Okay, so this is some applications. So this was sort of this visualization business. Here is actually a very interesting application with this guy's Carrazza Andreacci from the Stanford Biomotion Lab came up with. Let me show. Okay, so here is a walking guy. So what they have actually a 3D setup. So this is actually 3D imaging. They have a 3D setup. And what do? They're actually interested in the markerless segmentation. So they want to actually, what they're interested in, they're in biophysics, right? So they want to segment out the joints. And they want to do it, so the traditional way is to put markers on your body, but there are some problems with that. Ideally, it's much nicer to do it without markers. In some situations, of course, you can't even put markers. So what they're interested in is having some algorithm for this markerless joint segmentation. And they're interested in things like angles of various joints. And so the observation here is the following. And so they have this guy walking, and it's a 3D setup. There is a bunch of cameras. So they get the 3D location for each point. So basically, a body is represented at each time is represented by a point cloud, right? And so this is a point. Now, what about the colors? So the colors are sort of the nice part. It's pretty, right? Green and red. So the colors are the following. So you take the Laplace operator. So you have this point cloud. You can do the procedure which I just described. You can take the eigenvector. Eigenvector of a Laplacian, say third. This I think fourth or fifth, I forget. Is a function on your point cloud. Yeah. Do you agree? So now here is the interesting thing. This function on the point cloud is actually the following. You have, what happens when you move? Think about this. You actually, your body doesn't stretch, your skin doesn't stretch, right? So it's actually an isometric transformation in time. So meaning that the distance between this point and this point as I move doesn't, even though when I do this, right, the shortest distance doesn't change, the geodesic distance doesn't change at all.
Unless you're a matrix.
Well, maybe if you're extremely flexible. Well, in any case, most of us are not. In any case, so skin generally stretches very little, so it's an isometric transformation. And the Laplace operator is an isometric invariant. So it's actually a little bit like you were showing to me. And so this eigenfunction of the Laplacians actually are invariant of time. So if you take a value at this point of the Laplacian, it will be the same throughout. So to do segmentation, you just have to figure out where the joint is at some point in time, and then you just can follow it throughout, which is not so easy to do directly from images, right? Because it's not clear where the joint is. So you just have to segment it at one time, and then you just follow it through, and that's it. Of course, they use more than one eigenfunction. And sort of the thing to observe from here is that the colors, this is the values of this eigenfunction, they don't change as the guy moves, right? Each point stays the same, like the hand stays green consistently. Okay? So that I don't know. I found it nice. Okay, and there are other things too. All right, so now so it's already 46. So how much more time do I have? It's I think 46 past, so should I?
Maybe 15 minutes.
Okay, so I'll go until 2. Okay, so now I want to sort of, so this was one thing. Now I want to talk about, so this was basically about this dimensionality reduction and what it can do. Now I actually want to talk about semi-supervised learning, which in a sense our sort of main application of in this setting. Okay. So what is semi-supervised learning? So, you know, ordinary supervised, fully supervised learning, when you have x, I, y, i's, right? You have x and you have some output, and you want, given a new function, a new example, you want to classify this example, right? I have images, I have labels. I want to classify a new image. Now, what if I have unlabeled data? What if, in addition to these examples, which I know the labels of, I have a million examples which I don't know the labels of, but I have a lot of examples, right? What does it tell me? That tells me something about this manifold, but it doesn't tell me anything about the function on the manifold. So the idea is, maybe you can reconstruct this manifold in some sense, and then you use this guy, the y's, to reconstruct the function. So you use unlabeled data to reconstruct the manifold, and you use labeled data to reconstruct the function. And to do this, so we proposed a couple of ways. I'll just talk about this way because this is kind of a nice way to do it, it seems. So this is the sort of, so you're familiar with support vector machines and regularization and that sort of thing. So it's sort of least squares regularization looks, I use least squares here because it's kind of nicer to write, but you can use the hinge laws for support vector machines if you prefer. It's something like this. You have x, y, and i's. So you have fit to the data, fxi plus yi, and you have the penalty, some sort of norm of f in some space, some appropriate space. And this is reproducing kernel Hilbert space. So what does this do? This makes sure that at each xi, at each point which we observe, the output should be close. The output of my function should be close to the desired output, right? I penalize when it's far. This makes sure that this function doesn't vary too much. It doesn't, go like this, because of course I can fit anything, but I don't want to fit anything with something which oscillates like crazy. So in a sense, this f, this norm, incorporates some sort of smoothness assumption, some prior belief about the nice class of functions, and this of course makes sure that we are close to the desired output on the points which we know. So this is fit to data plus smoothness. Now, the nice thing about this, the good thing about this reproducing kernel Hilbert spaces is that suppose this is a Gaussian kernel, then actually, even though this optimization over some nice infinite dimensional space, the result of this optimization is actually very nice. It's a finite sum of Gaussians, assuming the Gaussian kernel. And it's just basically a sum of bumps over this label point, and the coefficients for the quadratic laws are just given by some linear equation. And for support vector machines, you can do quadratic programming to find coefficients. Okay? So this is the sort of the state of affairs in SVM. RLS, regularized least squares. Now, okay, I'll skip this. What did we suggest that this is this part, and because we suggested actually doing the following: to skip that and add an extra penalty, and this penalty will actually reflect our understanding of the manifold. In what way does it reflect our understanding of the manifold? What do we want from our function? Well, we just said there was some sort of manifold assumption, right? Which says that the function doesn't vary too much over the manifold. We have a way for controlling it using the Laplacian. So we use unlabeled data to reconstruct the Laplacian. We put it here, and we put it as a penalty. And this becomes this sort of matrix multiplication. So now the total optimization problem is the following. You have fit to the data, you have some sort of extrinsic smoothness, and you have intrinsic smoothness here. In intrinsic, I mean it's on the manifold. This is given by unlabeled data, and this is on the whole space. And the nice thing for least squares, you actually just solve it. It's a linear system. And you get the direct coefficients. And the solution is going to be, it's again this magic of RKHS. You actually get a solution. Even though it's an infinite dimensional optimization, you get an explicit solution. It's a sum, for example, if the kernel is Gaussian, it's a sum of Gaussians at each labeled now and unlabeled point. And the coefficient you can compute. And for SVM, there is a similar problem which you can write, a quadratic optimization problem. So, okay, and this works well, actually. This works quite well. So these are some examples. So there are some other ways of doing it, but just compare how. So this is a bunch of data sets, and this is SVMs with full labels, and this is SVMs with just a few labels. And this is what we get by adding unlabeled data. So this is kind of the improvement is going from here to here. Okay, and I mean it works it is quite competitive to everything else which exists. But more interestingly, it is.
So what do those numbers represent?
Error rates. I'm sorry. That's an important part of interpreting this table. Some mysterious tables with numbers, right? unknown. Yeah. Well, but in any case, we see that, in some cases you go like, from 24% to 3% or something. So you get, the interesting thing is you get improvement, always you get improvement. So you always get improvement. Sometimes they're not huge, like from 8 to 5. But sometimes they're really large, this and this. This is not huge, but this is quite large, and so on, you see.
And when do you get the large discrepancy or large change in error there?
It's not completely clear. It's just in some data sets we just get small improvement on some. We always see improvements.
But it doesn't. So it doesn't
always,
really go with the structure of your data to begin with.
It must have something to do with the structure, but since we don't have a good grasp of what the structure is, the only thing we see is this estimation thing. So it's something about the structure being nicely separated in some way, but it's not clear. I mean, you can imagine, for example, if it's just two separate manifolds, right? And this is class 1, this is class 2, this would would work amazingly well. So maybe in something like this, maybe something like this happens, right? Because you see that actually FEM with full labels gets 0% error. So probably they're fully separable. And probably they find it quite well, the structure. But in other examples, it's not. I mean, it's not completely clear. Like this is actually handwritten digits USPS. So you get quite a good improvement. Well, I mean, quite far from full labels, but much better than that. So on handwritten digits, it generally works pretty well.
So is that what USPS uses?
Yeah, USPS is the postal data set, handwritten digits, zip codes.
What do they do for the recognition?
I actually use some sort of neural network. Jan LeCun, he has this Linnets. At least part of it, I think, is processed by that. I don't know what else. But yeah, it's he has, but it's it's a highly hand-tuned architecture. So he spent like 10 years developing this. So it's a neural network which has been highly tuned. So this, of course, is not, this is sort of much more black box. The remarkable thing is actually, though maybe you use an SVM, and so maybe state of the art, like complete state of the art, is like 0.6, 0.7% error rate, and on MNIST, not on this actually is high. So MNIST is like one of the handwritten digit data sets, and amazingly, you can just take a SVM out of the box if you take a fully labeled, and you get pretty close. You get not. I mean, okay, you get maybe 1 point something error, but it is pretty good just out of the box. And considering that those things were really tuned. But in fact, there were some people claim that some methods do better than human, which is interesting. Okay.
How do they know?
How do they know that they do better than humans? that I don't understand. Because there are some God-given labels, right? That's a very good question. Okay, so maybe I'll just say a few words about some theory, and we've actually spent quite a bit of time doing the theory, but it comes at the end. Though basically what we can show now, and this is quite recent actually, this result, is this is Party and myself. We can show that in some sense eigenvectors of this Laplace matrix can be shown to converge to the true eigenfunction of the Laplace operator on the manifold. So, it's not just some sort of random heuristic which sort of works. There is actually, if you believe that there is a manifold, if really there is a manifold, and if you really can sample from the manifold, then you can actually show this convergence. And yeah, so there were earlier versions of this, and there was one in my thesis, for example. you can show convergence for a fixed function, but now we actually have convergence for the whole spectrum for each fixed eigenfunction.
And this is regardless of what. I guess the question that comes to mind at first is how do you construct the graph to begin with? Because you start out with, obviously you start out with a point cloud, and you have to basically structure this graph.
Mm-hmm.
How do you pick? It's independent of that structure that
Well,
you choose?
so basically, in the limit, it is pretty much independent. So you can show that there is some way to choose this t parameter, right? The width of the Gaussian you use for the weights, such that this will converge. So in the limit, it is independent. In practice, you just have to be careful. In practice, just doing nearest neighbor sometimes works well. When you don't even do Gaussian, you can just take, just connect this and put 1 or 0. Sort of hard threshold Gaussian. Or you just do nearest neighbors or something. That quite often works well. So there are various things which you can try, and then you try a few things and see which one is best. But there is no, it's like all this parameters.
Do you limit the degree of your vertices? The order of your vertices?
Well, so typically what we've been doing, we've just been taking a few nearest neighbors. Take 10 nearest neighbors and maybe just do hard thresholding, 1 or 0, or put a Gaussian on this.
Do you upper bound?
Just take 10 nearest neighbors.
The degree of your any given node, any given vertex.
No, we would just construct the graph by taking 10 nearest neighbors and symmetrizing it. But the thing is, there is another advantage with taking nearest neighbors because you end up with a sparse matrix. So that if you take eigenfunctions of that, for example, it's far faster.
So why not take, for instance, the minimum spanning tree like people do, for instance?
But what do you mean, why not take it?
Well, I mean, people have also looked at this problem from a minimum spanning tree.
Well, there is this guy, Al Hero, at Michigan. So, but they just estimate dimensionality, right? They don't do this.
Yeah, he hasn't applied it, but I'm just,
right.
I'm a sort of a hypothetical question.
So they have this nice way of estimating dimensionality from your data.
Right.
And they basically build a spanning tree, and then they basically look at the spanning tree and so on. But here you cannot really, I mean, you have to build this Laplacian, right? You have to do this, right? You cannot, spanning tree will not help you in this case, right? You have to choose these weights in some way. So nearest neighbors is a good heuristic. You end up with a sparse matrix, so you can quickly, so for example, we were able to do, find eigenfunctions. So there is another way of doing the semi-supervised using eigenvectors of this Laplace matrix. It's similar, but a bit different. And we were able to do something like 80,000 points because it's a sparse matrix, so you can do quite huge matrices. Like 1,000 eigenvectors of an 80,000 by 80,000 matrix. Because as long as it's reasonably sparse, it works. Okay, so this may be, perhaps I should finish. I mean, there are quite a few other things which can, this is sort of a long story, but there are other things which can be said. But here, basically, I mean, in a sense, the sort of the take-home thing from here that I mean the geometry is useful. That's to summarize this talk in 3 words. That would be it.
Let's thank our speaker. Any questions? Okay, to follow up on this thing. So, for instance, you were talking about these fairly large matrices that you deal with in practice. What kind of time are we talking about here? I mean, execution time for, say, maybe not an 80,000 point, but
So it depends on different algorithms. So that one, the sort of what we call Laplacian SVM. So it gets slow once you get to, I mean, more than 10,000 is hard.
But for instance, I'm thinking more specifically in terms of the example there that you showed out of Stanford, where they,
Oh, those are easy to do. Because then you just compute eigenvectors. Those are easy actually, because here the problem is that are full.
You start out with a point cloud, right?
Yeah.
So
10,000 is nothing, yeah, because it's sparse, right? When the
Right.
way you build it is sparse.
Right.
So 10,000 you can do no problem. 10,000 you can sort of, the limit of what you can do is a full matrix. But for sparse one, you would say probably 100,000 is possible. So I think the actual number of points in the point clouds is an order of a couple thousand. So for that,
in that human.
in that guy
Yeah.
the walking guy. Yeah, so for a few thousand, it's just like that, 20 seconds, I don't know. It's a sparse matrix, it just sort of flies. Yeah, once you get to the order of 100,000, sparse becomes slow. So Vikas Singhwani, he recently has some work on actually doing it for very large data sets, like up to millions. So he has methods of.
So they use those things for
optimizations.
like tracking also or something?
Well, so they were using it for actually joint segmentation. Those guys to do joints, segment out the joints.
Yeah, what do they do with that?
They want to figure out. Well, they basically have. So by physics, they want to see various positions of joint in various situations, and basically they have a model. They fit so once they segment joint, they just fit cylinders here,
I see.
and then they can do various things with that. But they need to know where to fit those cylinders.
Oh, this is like for rehabilitation people.
Yeah. So ideally, you would want to have something like that, right? And
Particularly like in sports medicine.
right, sports medicine, that's the sort of thing I think it's probably still quite far from actually, being in medicine, but that's and and the problem with markers is that, for example, in sports, when people play like basketball, you can just put markers on them.
Right.
You want to have some methods and you want to see when they get injured and so on.
Any other questions? All right, let's thank our speaker again. That's actually fascinating. I've read actually.